What I wanted to do with Big O today is, I think that the hardest thing in that was doing induction proofs with inequalities. Because we know the definition of Big O, right? What is the definition of Big O? F is Big O of G if there exists a constant C so that f of x is less than or equal to Cg of x for all x where x is greater than or equal to k. Right? So I also have to actually say there exists a k. Right? Doesn't matter where I put the there exists a k. As long as I have a c and a k that makes this inequality true, then f is in Big O of G. Okay, so sometimes we have to actually prove that inequalities are true. And that's the hardest thing to do in induction. So let's prove one. So let's prove that 5 log n is Big O of n. So in an induction proof, I have to start with a basis and assume and prove. So if I'm proving this, I have to prove an inequality. 5 log n is less than or equal to c times n, where n is greater or equal to k. So what's k going to be in my induction proof? It'll be the basis, right? And what about c? I can pick it to be anything I want as long as I pick it and stick with it through the whole proof. So what number would you pick to make it easy? I would pick 5, so I can divide it out, and then I have no more 5s in my proof. Right? That's what I would pick. So let's pick that. Okay, so let's say c equals 5, and then k would be what? When is log n less than or equal to n? As long as n is at least 1, right? Log of 1 is 0. I can pick n equals 1. But your instinct to pick 2 is fine, right? It's okay to pick a bigger number. Picking 2 is good because then you never divide by 0, right? So if you have any divisions, you do want to pick 2 to use for your algebra. All right, so we're going to do this proof by induction. We're going to prove that log n is less than or equal to n for all n, greater than or equal to 1. So our basis is going to be n equals 1. So we want to show that log 1 is less than or equal to 1. Well, this is 0, so that's true. So writing basis assume proof is no different for inequality proofs than anything else. It's the part after this that's different. But it works a lot like the regular induction proofs that we've done with equalities before. So we want to start with one of the sides that's easy to transform from the proof statement into the assumed statement, because we want to use what we know from the assumed statement. In this case, logs are hard to transform, right, if I have an addition inside. So I want to start with the right-hand side. So I'm actually going to end up proving, I'm going to reverse these. Just so we're used to working with the side we're going to start with. Okay, so we'll say that n plus 1 from the assumed step, the induction step, we know that's greater than or equal to log of n plus 1. That's this inequality adding 1 on both sides. So this is the left-hand side of what I want to prove. So now I just have to get this right-hand side to be what I want. So now I want instead of this stuff over here, I want that to be greater or equal to log of n plus 1, because that's what I want on the right-hand side of my inequality. And intuitively, this should make sense, right? Because n plus 1 and n are about the same size. If you take the log, that's a number that's way smaller than n or n plus 1. And then adding 1 to it ought to be bigger than taking the log of one bigger number, right? So when you do these proofs, it should make sense. Whatever you're trying to prove, it should make sense that it's true. Okay, now let's see. We want log of n plus 1 to be bigger than log of n plus 1. This is, if you don't know what to do, then you can do an induction proof. Okay, so if it's something that you can't see, like what to do, you know, ahead of time, then you can do an induction proof. So let's do that. Basis.
We were doing
Hmm?
I thought we were doing one of them.
Yeah, we'll do another induction proof. So I want to prove this statement. So I can do another induction proof. I'll do it on another sheet.
You can set 1 equals log, whatever the log n the basis is. For example, if the base is 10, it equals log 10. Then it equals log n plus log 10. That equals log n times 10. Is that right? That will get a proof.
I mean, probably I don't need to do an induction proof for this.
Okay.
I could raise both sides to the 2, right? 2 to the both sides. Let's try that. See what we get. On the right-hand side, I get n plus 1, right? On this side, I can separate this, right? 2 log n times 2 to the 1. That's the reason for that. That's not good.
Yeah.
Did I do something wrong?
2 log n.
2 to the 1. Sorry, 2 to the 1. That's good. Okay. Brain dead for a second there. 2 to the 1 times that. So there's a proof. I don't have to do an induction proof. Any way you want to do a proof works. So this is like a little sub-proof for the thing that I wanted to prove. So if you read it that way, it looks like a proof that your geometry teacher would like. Did you guys ever have math teachers that were like, don't start with what you want to prove? Okay, I say just read it backwards. Okay, so there's a proof. So if that's true, then what? So I have this first statement here and the second statement here. If I combine those, I get what? Using something like hypothetical syllogism, kind of, or transitivity. If I know n plus 1 is bigger than log n plus 1, and I know log of n plus 1 is greater or equal to log of the quantity n plus 1, then I know what? N plus 1 is greater than or equal to log of the quantity n plus 1. That's why I wanted this thing in the first place. Was because that's what I was trying to prove, was that I didn't care whether whether n plus 1 was bigger than log of n plus 1. I didn't care about that. I just got it from the assumed statement. What I cared about was this first thing being bigger than the last thing. So all you have to do is go over and do a side proof of this thing, and then you're done with your proof. So what you're doing in an induction proof is consecutively reducing your problem into something easier to solve. Right? I wanted to prove log of n is less than or equal to n for all n. So a problem easier to solve is to prove it for one step, because I can't write it for every single thing. That's why I do a basis, assume, prove. So I do a basis, assume, prove, and then I get to a part where, oh, I need to know something else. And then I can do any other kind of proof, even if it takes another induction proof here to prove whatever this is, then I can do that. So this is the magic step in an induction proof that has an inequality. That magic step is just to say, what is it that I want next that will give me what I want to prove? So I need to use my assume statement first to get the left-hand side or the right-hand side, whichever you're working with, of your proof statement. And then you will get an inequality that you'd like to be true, and then you try to prove that. And I promise I won't give you any in this class that you won't be able to do this way. Sometimes there are ones that are so tight, like these two things are so close together that you can't actually just have this function actually be in between them. Because sometimes you have to multiply by some really weird number to get it to fit in between. I'm not going to give you any that hard. Okay?
There's something down. Push it a little bit. Thank you.
So those two lines gave us what we wanted to prove. So then we were done with the proof. So having our little side proof also on the paper at the same time. So the only other thing that you had problems with on Big O on the homework that Andy told me was what to do when you had a product of two things. And I hate to even say this because what you do when you have a product of two things is absolutely nothing. So if I have n times log of n and I ask you what's the big O of that, you say n log n. It's a product. I only do stuff with big O with what functions? Plus. Sums are the only thing I do anything with, and I drop constants. There's no constants, no sums, I'm done. As soon as you get to the point where there aren't any sums and aren't any constants, you're done. You can even leave some constants, right? I can leave these kind of constants, like up in the power. Okay? And I could even leave, this would be an acceptable big O also, because n plus 1 is significantly bigger than n factorial, right? So I wouldn't necessarily drop that plus 1. So otherwise, I'm going to drop numbers and I'm going to drop any pluses that I have. So given that, let's figure out the big O of this function. So first I figure out for every sum, I figure out the big O of that sum, right? So for this first one, what's the largest term? N squared. I can even ignore the rest. If I want the constants, I can do what? Replace every term with, leave the coefficient and replace it with n squared. So it would be n squared plus 5n squared plus 3n squared. So that would be 9n squared, and then I would drop the 9, right? But quick and dirty is just to circle the big one. And why do I have to be careful about circling the biggest one? If I have a number of terms that depends on n, I definitely need to replace them all and count them all up. Because if I have 1 plus 2 plus ... plus n, the big O of that is n squared. Right? So I can't just circle the n. So if I have more than a finite number of points, so I have a finite number, but if I have not a fixed number, I need to count up the terms, because there might be n of them. If the number of terms depends on n, you need to count them up. If it doesn't, you can just circle the biggest one. Okay, how about this one? e to the n. How about this one? Just n and cross out the 10. So what's the big O of this? N squared e to the n over n. I don't even care if you divide it out, but that's equal to n e to the n. So you have nothing left to do. After you're done with the sums and the constants, that's it. And if you have to do a proof, you just do what I said and replace everything with the largest. Any questions about that? So what is big omega? Big O is upper bound, and big omega is lower bound, right? So it's basically the same as big O, except your inequality goes the opposite direction, right? And what about big theta? So in big omega, all I have to remember is it goes greater than instead of less than. And big theta is big O intersect big omega. So F and G, if two things are in big theta, that means they're approximately the same size. Because if one can be both an upper and a lower bound for the other one, that means that I can multiply one of them by a constant and then by a smaller constant and sort of like trap the other one in between. So that's what that means. Big theta means you have a graph like this. I can take G and F and multiply one of them by a constant to get a graph like this. So I have like big squiggly one on both ends, and I have the other one in the middle. So I have like C1F, C2F, and G can be in the middle. So I can bound G by constants times F. That means they have to be about the same size, right? So they can't be growing at different rates because eventually something would cross.